Hello everyone, in this control engineering and control theory tutorial you will learn how to design and test observers of dynamical systems in MATLAB. We will focus on linear dynamical systems in the state space form. We will explain how to design observers by using the pole placement method and how to numerically implement and test the performance of observers in MATLAB. But before I start with explanations, I need to mention the following. It took me a significant amount of time, energy and planning to create this video tutorial, as well as more than 450 video tutorials that you can find on my YouTube channel. And consequently, I kindly ask you to press the like and subscribe buttons. Thanks a lot. Here is a brief outline of this video tutorial. First, we briefly explain the basics of observers for linear dynamical systems in the state space form. Then, we explain how to design the observer gain matrices by using the pole placement method. And finally, we explain how to implement observers in MATLAB. As a test case, we will consider a mass spring damper system shown over here. Okay, let's start. We consider a linear state space model of a dynamical system shown over here. Over here, x is the state vector, u is the control input vector, y is the output vector, and a, b, and c are the system matrices. Here, it should be emphasized that only the output vector y can be observed. However, in many applications, we would like to have access to the full state vector x. For example, in order to design a state feedback control algorithm, we need to have information about the state vector x. There are also many other scenarios in which we need information about the full state vector x. This motivates us to develop an algorithm that will estimate the state vector x from the time sequence of the observed output vector y. Such an algorithm is called an observer in the control engineering literature. To summarize, the main goal of our observer is to estimate the state of the system from the measurements of the output vector y. The observer of the system is given by this state equation, and here is the block diagram of the observer. Let us explain this notation. X hat is actually the state of the observer. That is, the hat notation denotes the state of the observer. The state of the observer is at the same time an estimate of the true system state. The observer has two inputs, u and y. U is the control input of the system and y is the output of the system. Again, the inputs of the observer are input u and the output y. Keep in mind that. The matrix L that you can see over here is the observer gain matrix. Our goal is to design this matrix such that the state of the observer x hat asymptotically tracks the state of the system x. Equivalently, we want to design the observer gain matrix L such that the state estimation error x minus x hat asymptotically approaches 0. As we explain later on, this means that the closed-loop dynamics of the observer has to be stable. Next, let's learn how to design and simulate the state observer in MATLAB by using the pole placement method. First, let us define the estimation error. Here is the estimation error. The estimation error is the difference between the true state of the system, x of t, and the observer state, that is, the estimate of the state. Now, let us take the first derivative of this equation. As the consequence, we obtain this equation. Now, let's substitute the system dynamics in this equation. As the result, we obtain this part, and let's substitute the observer dynamics in this equation. The observer dynamics is given over here. Then, by substituting this equation over here, we obtain this equation. Now let us rearrange this equation. How to do that? Well, we can observe over here that we have ax, and over here we have minus ax hat. So we can take a out, and inside of parentheses we have x minus x hat. Then we can observe this part over here, ly and cx hat. Instead of y, that is the output of the system, we can write cx. And consequently we obtain this part. Observe over here that bu and bu are cancelled. Then, by rearranging this equation, we obtain this equation, and finally we obtain this equation. Next, let's use the definition of the error given over here. We can observe that this part is actually the error, and we can write instead of this part the error. This equation represents the closed-loop observer dynamics. The goal of the observer design is to select the matrix L such that the closed-loop system given over here is asymptotically stable. This means that for any initial value of the error will asymptotically approach 0. This means that our state estimate will asymptotically approach to the true system state. The closed-loop stability of the system is achieved by using the pole placement method. The idea is to design the matrix L such that the eigenvalues of the matrix A minus LC are at prescribed locations that will guarantee asymptotic stability. From the linear systems theory, we know that if the poles of the closed-loop system are strictly in the left half of the complex plane, the system, or better to say the closed-loop system, is asymptotically stable, and consequently the goal is to select the matrix L such that the eigenvalues of the matrix A minus LC are strictly in the left half of the complex plane. As we will thoroughly explain later on, MATLAB has a function called place. This function is used to perform pole placement. However, this function is designed for feedback control problems where the goal is to compute the feedback control matrix K such that the poles of the closed-loop system A minus BK are at prescribed locations. However, our observer design problem looks a bit different. Our closed-loop matrix looks like this. And notice immediately over here the difference. We can see that our design matrix L is over here. However, in the pole placement method performed by MATLAB, the design matrix K is over here. That is, the positions of the L and K matrices are different. However, we can still use MATLAB's place function by observing the following. First of all, it's a very well-known fact in linear algebra and control theory that the matrix and its transpose have the same set of eigenvalues. This means that our original closed-loop matrix A minus LC and its transpose given by this equation have the same set of eigenvalues. Next, let's compare the transpose of A minus LC given by this equation with this matrix A minus BK that's used in the pole placement method by MATLAB. We can immediately observe the following. The place of L transpose is the place of K. So K plays the role of L transpose, or other way around. L transpose plays the role of K. Very good. Then the position of C transpose is the position of B. So C transpose plays the roles of B, and A transpose plays the role of A. So this matrix has the same structure of this matrix. And we can use the pole placement method and the MATLAB's function place to assign the poles of this matrix. That is, we will design the matrix L transpose such that the eigenvalues of this matrix are at the desired locations. This means that the eigenvalues of this matrix will be at the desired location simply because this matrix and this matrix have the same set of eigenvalues. Before we start with MATLAB coding, we need to consider a test case. As a test case, we consider this system. The system consists of two objects with masses m1 and m2 that are connected by two springs and dampers. The spring constants are k1 and k2, and the damping constants are d1 and d2. There is external force F that's used to control the system. The variables S1 and S2 are displacement of the corresponding objects from their equilibrium positions. We assume that only the displacement S1 can be observed. That is, we assume that there is a sensor over here that measures the displacement of the first object. In our previous tutorial, which can be found over here, that is, you can click over here, and I will provide a link in the description below this video tutorial, we derived the state space model of this double mass spring damper system. Here, for brevity, I will just briefly summarize the state space model. The state space model is derived by assigning the following state space variable. x1 is s1, that is the position of the first object, x2 is s1 dot, that is the velocity of the first object, x3 is s2, that is the position of the second object, and x4 is s2 dot, that is the velocity of the second object. By using these state space variables and by using Newton's second law, we obtain this state space model. Over here, bold x is the state vector that takes into account all the state space variables x1, x2, x3, and x4. U is the control input vector, and it's a scalar only equal to the external force F. This is our A matrix, where the system parameters such as masses, damping constants, and spring constants play a very important role in this matrix. Here is the B matrix, and finally here is the output matrix C. The structure of this matrix means that we only observe the position of the first object. Our task is to model and simulate this mass spring damper system in MATLAB. That's the first task. Once we do that, we will design the observer. So let's start with MATLAB coding. Okay, let's start with MATLAB implementation. The first step is to define our state space model. To do that, we need to define the system parameters. Here they are: mass m1, mass m2. Mass m1, mass m2. Then k1 and k2, spring constants, d1 and d2, damping constants. Next, we need to define our A matrix. Here's the A matrix, and here's the MATLAB definition of the A matrix. Here's the B matrix, here's the C matrix, and D matrix is empty. Now that we have our system matrices, let's define our system. I will type system1, and I will use the function ss for the state space model to define the state space model in MATLAB. I will type A, B, C, D, and that's it. That's our state space model. Let's see our state space model. Here it is. Perfect. Next, we need to simulate the state space model in order to generate data for our observer. To do that, we first need to define the time vector. The time vector will start from 0 with a step of 0.1 second, and the final time will be 5 seconds. Perfect. Let's define our control input sequence, that is the value of force at certain time steps. Input will be 10 times ones, and over here the ones will be of size time vector. So what I'm doing over here, I'm defining the input that's equal to 10, and 10 is constant. Consequently, I will compute the step response of the system. That is, I will simulate the system when the force of 10 newtons is applied for 5 seconds. Next, I need to select initial state for simulation. I will call the initial state as x0 true, and the initial state will be the following one: 3, 1, minus 3, and minus 2. S1 is 3, S1 dot is 1, S2 is minus 3, and S2 dot is minus 2. Next, let's simulate our system. To simulate the system, we will use the function LSIM. The first input argument of LSIM is our system. In our case, it's system 1, that is our state space model. The second input argument is the input sequence used for simulation. In our case, it's input. The third input argument is time vector. And the last input argument is our initial state, x0 true. The outputs, that is the values returned by LSIM, are the output of the system. I will denote it by the y true, time used in simulation, and the state sequence. Okay, so let's simulate our system. Perfect. Let's look at the dimensions of the matrices. For example, if we type size x true, we will obtain a vector with 4 columns and 51 rows. The columns correspond to the states x1, x2, x3, and x4, and the rows are actually the time samples. Perfect. Let us now plot the results. Let's see the system's response. To do that, we need to create a figure. Then over here I will use hold on, and I will type plot time true, and over here I will plot x true, and I will plot, for example, only the first state. Let's see the first state. Okay, here it is. We can see the states start from 3, and the system is lightly damped, and we will see oscillations. Perfect. The next step is to design our observer. The first step is to select desired pole locations for the closed loop matrix A minus LC. Okay, so I will create a vector pole location, and I will select the following poles. The first pole will be at -4 on the real axis, the second pole will be at -6, and then I will have 2 conjugate complex poles. One will be at -2 plus 2i, where I is the imaginary unit, and another one will be a conjugate of this pole. It will be at -2 minus 2i. Perfect. And note over here that all the poles are strictly in the left half of the complex plane. This is because we want to make sure that our system is asymptotically stable. So keep in mind that. The next step is to design the observer gain matrix L. For that purpose, we will be using the function place. So type place over here and inform yourself about the place command or place function. It's written over here. Place computes a state feedback matrix K such that the eigenvalues of A minus Bk are those specified in the vector P. So the inputs are the matrix A, the matrix B, and this vector P that denotes the locations of the desired closed loop poles. So let's use that function. We'll type over here the following. Place. And watch out over here. As we explained previously, instead of A, we need to type A transpose. Instead of B, we need to type C transpose. And over here, we need to specify pole location. This function, as explained previously, will not return L. The function will return L transpose. Then, after computing L transpose, L will be equal simply to L transpose, transpose. And that's it. Okay, so let's run this piece of code and let's investigate and see the result. Okay, How can we verify these computations? Well, we can compute the closed loop matrix. It's equal to A minus L multiplying C. And let's compute the eigenvalues of this matrix. First of all, let us define this vector. Pole placed will be equal to the returned eigenvalues. Okay, so this is pole placed. Then, let's compare pole placed with pole locations. To do that, let's type this. We can do this, sort, and let's sort pole placed. Then let's do this, minus sort pole locations, and let's see the result. Okay, so there's an issue over here. We'll probably need to transpose one of these variables. Yes, we'll need to do this. And let's see now the difference. Okay, we can see that the difference is really small. This is very important to keep in mind. The difference is in the order of 10 to the minus 13, and that's almost the numerical precision. Okay, the next step is to simulate our observer. So how to simulate the observer in MATLAB? Let's analyze our observer state equation. Here it is. Now, this equation can be written like this, or we can write the second equation in this form. Here's our A minus LC, this is the closed loop matrix, and over here we can see two terms, BU and LY. These two terms can be written together like this, and we can actually define a new matrix, B and L, this is a block matrix, and we define a new vector, U and Y. Now, this is a new state space model where now the input of this new state space model is this vector U and Y. Next, we need to define the output equation of our observer. Since we are designing the observer and in any moment we know x hat, we can simply say that the output equation of the observer is C0 multiplying the state of the observer, where C0 is the identity matrix. Note that we can always do that since we know x hat. Consequently, our observer state space model at the end of the day looks like this. A0 is our closed loop matrix, B0 is this block matrix with the blocks B and L, and C0 is the identity matrix. So let's simulate this observer in MATLAB. So what's the first step? Let's define the observer matrices. Let's call A observer, and the A observer is a closed loop. Then B observer is actually, let's look here, B and L. This is a block matrix, keep in mind that. Then, let's go further. What's the C observer? C observer is simple identity matrix. D observer is an empty matrix. Let's define our observer. Sys, let's call it observer. And it's equal to the state space model, and we just specify it. A observer, B observer, C observer, and D observer. Perfect. However, to simulate this observer, we need to define a new input sequence corresponding to this vector z. The vector z contains two entries, u and y. Consequently, our new input time sequence will consist of the time sequence corresponding to u and the time sequence corresponding to y. To do that, let's define a new vector and let's call it input uy, and this input is equal to input, where the input is actually the true input, or better to say true control input of our system, and the output should actually be the simulated output of the system. The simulated output of the system is y true. And over here you have to be very careful. Let's look into dimensions of y true. The dimensions of y true is 51 and 1. Let's see the dimensions of the input. 151. Consequently, we need actually to transpose our output. So we need to type this y true, and we need to transpose. Okay, so let's look into our input now. Let's type size input uy. Here it is. Perfect. It contains 2 rows and 51 columns. The first row corresponds to u, the second row corresponds to y. Perfect. Before we simulate the observer, we need to select the initial state of the observer. The initial state of the observer is just our guess of the true initial state. And I will call it x0 observer. x0 observer, let's say, for example, is 0, 0, 0, 0. All zeros. Okay, now let's call LSIM. And over here, the first input is our state space model. Then the second input argument is our control input. Here it is, and let's do this. Then the third input argument is time vector for simulation. That's the same vector that we used to simulate our original system. And the last input argument of LSIM is the initial state of the observer. LSIM will return the following time sequences. Output of the observer, time observer, that is the time used for simulation. Let me expand this. And the third output will be the time sequence of the observer. Perfect. Let us now simulate the observer and let's see the results. Okay, now let's compare the state of the observer with the state of our true system. Consequently, let's open a new figure. Let's do hold on. And over here, let's plot. First of all, let's plot the time on the x-axis and x true. And let's select, for example, the second state. And let's select the color to be, for example, red. This is the true state sequence number 2. That is x2 of our system. Let's look into the state of the observer. Again, here we need time vector. Then over here, we need to specify the state of the observer. Let's select the corresponding state. And let's select the color to be blue. Okay, and that's it. Let's see the result. Voila, here it is. Let's analyze this graph. So what's happening over here? Let's see. The red line is actually the state of the system. We can see that the state evolves like this, and this is the second state. That is the velocity of the first object. And this is the state of the observer. The state of the observer starts from 0, and first it has some overshoot. However, after some time it approaches the state and it asymptotically tracks the state. Perfect. This is very, very important. This means that our observer is actually properly designed. You can verify these graphs by, for example, selecting different states. Let's select x4 and let's see what happens with the x4. x4 is the velocity of the second object. Again, after some initial transient period, the observer will follow our state. Perfect. You can improve these graphs by, for example, changing the eigenvalues of the closed loop system. For example, we can make the tracking performance to be faster if we push these poles further left. So let's see what will happen. For example, this pole can be at minus 12 and this pole can be at minus 16. Now the observer will be very fast. So let's see the performance. Okay, we need to close this graph since MATLAB is memorizing everything, and here it is. You see how fast is the observer over here. Okay, that would be all for today. I hope that you like this video. If you like the videos I'm creating, please press the like and subscribe buttons. Thanks a lot and have a nice day.